Alright, so we're back at 4.4, problem number 2, part 2. Last we found local, last time we found inflection points, now we're looking at maximums and minimums. So, we set the first derivative equal to 0, as we've done so many times, and then we solve for that, and we find that the arc cosine of minus 1/2 equals 6x. So we go ahead and we look on a unit circle. I wish I could show you, but I'm just looking at it right now. So, I see that I'm looking for when the output of cosine is minus 1/2. Well, on my unit circle, the x-coordinate is my cosine. So I see that there's one point at which x equals minus 1/2 on the unit circle at 2 pi thirds. And then I also see that there's another point at 4 pi thirds, which we can also call negative 2 pi thirds because of symmetry. So in other words, if you start at the 0 line on the unit circle, going to 2 pi thirds counterclockwise is positive 2 pi thirds. Going 2 pi thirds counterclockwise is negative 2 pi thirds. So we have one of the values is minus 2 pi thirds, one of them is 2 pi thirds positive. And if you'll recall that every single especially cosine, but almost all trig functions, they repeat every 2 pi. So we need to add to this. So we need to take negative 2 pi thirds and add 2 pi, because that's when that value will repeat. And we'll rationalize the denominator, making 2 pi, 6 pi thirds. Now, negative 2 pi thirds plus 6 pi thirds equals 4 pi thirds. So you can see that there. So that would go up here, 4 pi thirds. And then what if we take 2 pi thirds and subtract 2 pi? We'll rationalize this. 2 pi is the same as 6 over 3 pi. So 2 pi minus 6 pi equals minus 4 pi thirds. And so you'll notice a pattern here, although it's a little more complex than the pattern in the last video. The pattern here is that these infinite solutions are equal to 2n pi over 3. And over here it's negative 2n pi over 3, and that's our set. And you can test this for yourself. If I plugged in 1 for n, 2n is 2 pi thirds, that's this value. If I plug in minus 1 for n, I get minus 2 pi thirds. If I plug in 2 for n, I get 4 pi thirds, and so on. So there are infinitely many solutions extending in either direction. Now remember, this set of numbers is equal to 6x, and we want to solve for x and get it by itself. So we're going to divide everything by 6. And you'll notice that what you end up with is 2n pi, negative 2n pi, divided by 18, because 3 times 6 is 18, comma negative 4 pi 18, comma negative 2 pi 18, and all the denominators become 18. All the way up to 2n pi divided by 18, and there's our new set. Now what we need to figure out is how much of this set that x equals to actually lies in this interval. So you remember in last video we did an approximation for 2 pi ninths. The interval was roughly between negative 0.698 and positive 0.698. So now we just need to figure out which one of these lie in that interval. And I'll let you do that yourself. 4 pi 18 is 0.698. So that's really close. 2 times pi ninths, 0.69813. Oh, well, that's clever. So these are the endpoints right here. This, because you could rewrite this as 2 pi ninths. 4 pi 18ths is 2 pi ninths. Negative 4 pi 18ths is negative 2 pi ninths. So technically these are the endpoints of the interval. These are the interval points. So we found what does lie in there is we found that x equals minus 2 pi ninths, and then x equals minus pi ninths, because 2 pi 18ths is pi ninths, positive pi ninths, and positive 2 pi ninths, these are all of our critical point values. Now, typically when you have an interval, you'll have to check for the interval endpoints being maximums or minimums. But since they're already included on our list of slopes of 0, right, where the tangent is 0, we won't actually need to worry about checking the interval endpoints. So now that we have all of our points, the hard stuff's over. Now we just need our original equation. Oh, and also, we should have checked to see which was a max or a min using the second derivative test, but we can get around that, and I'll show you how. So we're just going to start plugging these values in. So y of negative 2 pi ninths equals 3 times negative 2 pi ninths plus sine of 6 times negative 2 pi ninths. This is going to be a long problem. So let's see here. 6 times 2 is 12. What is that? Minus 4 thirds. 4 pi thirds. I think that's what it is. And this would be minus 6 pi ninths, which is equal to minus 2 pi thirds. And we're adding on the sine of negative 4 pi thirds. So we'll look on our unit circle. And at negative 4 pi thirds, which is also known as 2 pi thirds, our sine is root 3 over 2. So this is root 3 over 2. Negative 2 pi over 3 plus root 3 over 2 is what we get when we plug in negative 2 pi ninths into our original function. So here's our first order pair. The x value that we plugged in is minus 2 pi ninths, and the output is minus 2 pi thirds plus root 3 over 2. Now we're going to plug in our negative pi ninths. So y of negative pi ninths, plug it into our original equation, equals 3 times negative 3 pi ninths, 3 times negative pi ninths, plus sine of 6 times negative pi ninths, which of course equals what? Negative 2 pi thirds, negative 2 pi thirds, and this you can cancel this out. The 3 and the 9 goes to pi thirds minus pi thirds, because 3 ninths is equivalent to 1/3. Alright, so now what is sine of negative 2 pi thirds? Let's take a look on our unit circle. Negative 2 pi thirds, otherwise known as 4 pi thirds. The sign of that is negative 3 pi halves. So we have negative pi thirds minus root 3 over 2. Root 3 over 2, and that's equal to y when we plug in minus pi ninths. So there's our second ordered pair. It's going to be when we plug in negative pi ninths, and the output is negative pi thirds minus root 3 over 2. Alright, now we need to make some more space. We'll plug in another point. What about y when we plug in pi ninths? 3 times pi ninths is pi thirds, plus sine of 6 pi ninths. 6 pi ninths is 2 pi thirds. Sine of positive 2 pi thirds is root 3 over 2. So we end up with root 3 plus root 3 over 2 when we plug in pi ninths. So for that reason, our next ordered pair is when we plug in pi ninths, we get pi thirds plus root 3 over 2. And we just have one more left to go. So y of 2 pi ninths is our last one, equals 3 times 2 pi ninths, which is 6 pi ninths. 6 pi ninths plus 6 pi ninths is the same thing as 2 pi thirds, plus sine of 6 times positive 2 pi ninths. That would be 12 pi ninths, right? 2 times 6 is 12 pi ninths. 12 pi ninths is equivalent to 4 pi thirds. And then we'll check our unit circle for 4 pi thirds. So 4 pi thirds, our sign value is negative root 3 over 2. So we end up with, for this last value, when we plug in 2 pi ninths, we get out 2 pi thirds minus root 3 over 2. So we have all four max and minimum values. We don't know which are which yet, but we can kind of just figure that out without the second derivative. Normally I'd say take the second derivative and plug it in, but if we draw this graph out, we know that when the graph is 0, 3 times 0 is 0, and sine of 0 is 0. So we know we start at 0, 0. Now if we go to our first critical point, which is at positive pi ninths, we'll notice that we have pi thirds plus root 3 over 2. That's a positive number. And if we go to negative pi ninths, that's our second critical point. And at negative pi ninths, we have a negative number. Negative pi thirds minus root 3 over 2. So it's going to be exactly the same height as this in the opposite direction. Then, when we go to 2 pi ninths, a positive 2 pi ninths, let's see where we're at. So when we go to positive 2 pi ninths, we're at 2 times pi over 3. Right here, that's roughly 2.09, minus root 3 over 2, which is roughly 0.866. So this is actually a positive value, but not as positive as this value. So this is somewhere here, and likewise, due to symmetry, we're going to find that for negative 2 pi ninths, it's somewhere right here. And you can always plug these values in and check for yourself, or even graph it on like Desmos or your graphing calculator. Now what you'll find is that this is what the graph looks like. Now we're going to look at each point. This is 2 pi ninths, x equals 2 pi ninths. In relation to what's around it, it's actually a low point, right? Because if you walk away from it, you're going uphill. So 2 pi ninths, this one right here, is a minimum. Now from pi ninths, it looks like we're on top of a hill. So pi ninths is a maximum. I'll use red for maximum and black for minimum. If we look at negative pi ninths, it's low compared to everything around it. So negative pi ninths is a minimum. And if we look over here at negative 2 pi ninths, even though it's lower than positive 2 pi ninths, when you look at the relativity between it and what's around it, you'll notice that if you walk away from that point, you're going downhill, and therefore that's going to be called a local maximum. And so that's pretty much the end of this problem. I hope it helped. It's a pain in the ass. Yeah, just make sure you have your unit circle out. Use every technique possible, whether that's graphing or just plugging in values too. You could also use the second derivative test to figure out if these are maxes and mins using concavity, but that would have taken quite a while. So anyways, I hope this was helpful. I know there's a little bit of rambling, but it's not an easy problem to explain. So have a nice day, and I'll see you next time.